Particle size is one parameter which can influence many properties, and therefore accurate measurement of particle size is very important. In this video, we are going to learn about a particle size analysis technique which is very effective in measuring particle size. The technique is called dynamic light scattering, or DLS in short. Why it is called dynamic, that will be clear in a moment as we progress. So this technique uses the scattering of light by the particles to measure the particle size and the size distribution as well. And it is a common practice to disperse these particles in an appropriate solvent and get a good suspension, which is used to derive the particle size. Now, when the particles are suspended in a liquid, they are not stationary, and this motion of the particles in the solvent is known as the Brownian motion. So Brownian motion is nothing but the random motion of particles dispersed in a solvent in all directions, as you can see from this animation over here. And this motion arises due to the collision of particles with the solvent molecules. Now, this collision causes certain amount of energy transfer, which is more or less constant, and therefore the smaller particles will move faster compared to the larger ones, as you can see from this animation over here. Now, this velocity of the Brownian motion is defined by a property known as translational diffusion coefficient, written as D. And the D is related to the size of the particles by the Stokes-Einstein equation, which is given as follows, wherein dH is the hydrodynamic diameter. So here the particle size is defined by this hydrodynamic diameter, and I'll come to that in a moment. K, as you know, is the Boltzmann constant, and eta is the viscosity of the solvent. Now, this hydrodynamic diameter is defined as the diameter of a sphere that diffuses at the same rate as the particle being measured, right? So that is how the size of the particle in this case is defined, and that can be obtained from this Stokes-Einstein equation, wherein all the parameters such as K, T here is the absolute temperature, and eta are known. So if we can derive this translational diffusion coefficient D, then this particle size can be obtained from this equation. Okay. So this dynamic light scattering technique will essentially try and measure this diffusion coefficient so that we can use this Stokes-Einstein equation to derive the size of the particles. So in order to understand how that is done, you need to first understand what is the effect of this Brownian motion as far as the scattering of light by the particles is concerned. So let us try and understand as to what will happen to these scattered light beams when the particles are in Brownian motion. So let's say this is one scattered beam of light, and there is another one like this. So in this case, you can see that These two beams of light are in phase in the sense that positive to positive and negative to negative matches exactly as you can see over here, right? So these kind of waves are known to be in phase, and their intensity at any given point of time will be added to each other. And as a result of that, if you have the detector over here, the intensity which is received at the detector will be enhanced, and therefore this kind of interaction between waves is known as constructive interference, right? On the other hand, you can have two waves, one like this and the other one like this, wherein we can see the negative is coinciding with the positive, for these two beams. Okay, so in this case these two waves will cancel out each other, since, as I said, the negative is coinciding with the positive, and therefore the intensity which is received at the detector will be zero. And this kind of interference is therefore known as destructive interference, right? So therefore, the intensity which is received at the detector from the particles will form a pattern where the constructive interference will give rise to the bright spots in that pattern, and the destructive interference will give rise to the darker spots. And this kind of pattern is known as a speckle pattern. Now, if these particles are static, then the intensity of this speckle pattern will also be static or constant, right? The intensity will not be a function of time, or it is going to remain constant because the conditions are static. But now, as we have seen, when the particles are dispersed in a fluid, which is often the case for the particle size measurement by this DLS technique, the condition is dynamic because these particles are in Brownian motion, and as a result of that, their positions with respect to the detector are continuously changing, right? So the conditions here are dynamic, and that is how the name dynamic light scattering. So because of that, the intensity which is being received at the detector will fluctuate, right? As opposed to the static condition where the intensity remains constant. So this intensity fluctuation is what is being actually recorded by this technique in order to derive the particle size by deriving the translational diffusion coefficient. So in order to derive that, translational diffusion coefficient from this intensity data, we need to see how this intensity varies and what its relation is with the particle size. So if you look at the intensity variation, for the big particles, the variation is slower, or the frequency of this intensity fluctuation is lower. And on the other hand,
for smaller particles, this intensity fluctuation is quicker, or the frequency of this fluctuation is higher in case of smaller particles. So that is how you can see how this intensity fluctuation is related to the particle size and how the smaller particles can be distinguished from the bigger ones. Okay. And you can also realize by now the fact that these intensity fluctuations contain the time scale information of the particle motion. Okay. And from this information, we can actually derive the translational diffusion coefficient and then use it in the Stokes-Einstein equation to derive the particle size. Okay. So that is the idea behind this technique, to capture this intensity variation and use it to derive the particle size. However, in order to derive these intensity fluctuations, a certain method has to be used to derive the useful information out of this that can be finally used to derive the particle size. Okay. So the method which is used to derive this is known as autocorrelation. So let us see what is autocorrelation and how it is used to derive particle size from DLS experiments. So let's say you have a signal like this, okay, and there is some variation in the intensity, because this is what we are trying to capture, the intensity variation with respect to time. Now, the autocorrelation is derived on the basis of comparing this signal at a particular time t with the signal after a time interval delta t. Okay. So if you compare the signal intensity after a particular time interval delta t with the original signal at time t, then you would be looking at how this signal at time t plus delta t compares with the original signal at t. Okay. So if it compares well, then you can see that the correlation between these two signals is good. Okay. So that is how the correlation is derived when you compare the intensity of the signal after a particular time interval with that of the original signal at time t. Okay. So here you can see that the correlation of the original signal and the signal after a very small time interval delta t is quite good. And now if you increase this time interval, let's say to t plus 2 delta t now, you can still see some correlation, but as the time interval has increased, the correlation has decreased. Okay. So if you keep on increasing this time interval, the correlation will keep on decreasing. Okay. And this time interval across which this signal is compared with the original signal, that means this interval is known as the delay time, and it is written as tau. Okay. So if you continue to compare the signal at larger and larger time interval, there will be a time when the correlation will be completely lost. That means if you take time as a function and if you compare the signal from time at 0 to time at infinity, then you can see a decay in the correlation in this manner, where in the beginning, that means at time equals to 0, the correlation is quite good. And as you increase the time interval, the correlation will decrease, and at time infinity, when the time interval is large, then the correlation is completely lost. Okay. And one thing that you should note over here is that the time infinity is not really a very large time, because here we are talking about time intervals in microsecond or even nanoseconds. So a couple of seconds can be considered as the time infinity in this particular time scale that we use for doing DLS experiments. So this is the correlation function, which is the essence of this analysis that will ultimately lead us to the particle size which we are looking for. So to derive this decay in the correlation, there is an autocorrelation function which is first derived. So let us go ahead and see what is that and how that can be used to derive the particle size information. So it's about the decay in the correlation, or the decay rate that we are talking about. And we have already seen that the intensity fluctuations for the bigger particles is smaller. The frequency of these fluctuations is smaller compared to that for the smaller particles. And therefore, the decay in the correlation will be slower in case of the bigger particles. That means the decay rate will be smaller for bigger particles, whereas in case of smaller particles, because of this high rate of fluctuations, the decay rate will also be higher, and the correlation will be quickly lost in case of the small particles. Okay, so this is how, first of all, the small particles can be distinguished from the bigger particles, and this in fact forms the basis for the particle size distribution that can be obtained from this particular technique called DLS. Now, as I said, we need this autocorrelation function to be derived first. So this function is defined as a second order correlation function, which is given here in equation 1, wherein IT is the intensity at time t, and I t plus tau is the intensity after a time delay tau. Okay, so that is what we have been talking about. We are comparing the intensity at time t with that after a particular interval tau. Okay, so the second order autocorrelation function is given by this, and these braces that you see over here, these pointed brackets, these indicate averaging values over a period of time. So these values are actually averaged out over a period of time, which is used during the experiments. Now, if you consider the first order electric field correlation function G, or rather G1, this one indicates first order. Similarly, 2 over here indicates a second order correlation function. So this electric field is nothing but the electric field of the scattered light beam, and I will be the intensity of that electric field. Okay. So this first order correlation function of the electric field is defined as follows, like how it is defined for the second order correlation function. In a similar manner, the first order correlation function for the electric field can also be defined. Now, using this first order correlation function, the second order correlation function can be written as this, wherein B is the baseline correlation, that means the correlation at time infinity, and beta is the correlation function amplitude at tau equals to 0, that means beta is the intercept. Now, if you have a monodispersed sample, that means a sample having a single size, the correlation function will be an exponentially decaying function, which can be given as follows. So now this becomes exponential, as you can see from this exponential term over here. Where gamma is known as the decay constant or the decay rate, and it is related to D, the translational diffusion coefficient, and another parameter Q in this manner through equation 5. Q is known as the scattering wave vector, which is given as follows. So this contains the scattering angle theta as well as the wavelength lambda of the light. Okay, and the other term that you see over here, that is N, that is the refractive index of the solvent, which is being used to disperse the particles. Right, so what it essentially means is that the autocorrelation function or the intensity variations are measured across a wide range of theta, and when you do that and use that intensity data in the autocorrelation function, that will give you the intensity variation for particles of different sizes, right? And that is how the particle size information can be derived from this autocorrelation function, because it contains that size information and also the scattering angles. And it is also known that the scattering angles for the smaller particles is higher compared to the larger particles. The smaller particles scatter light at larger angles compared to larger particles, as you can see from this particular diagram over here, right? And for a polydispersed sample which contains particles of different sizes, which is generally the case, this generic form of the autocorrelation function can be used, where this term that you see over here is the sum of all the exponential decays contained in the autocorrelation function. So to summarize, we can say that the translational diffusion coefficient D, which is obtained by this autocorrelation analysis, can be simply put into that Stokes-Einstein equation here to derive the particle size. Okay, and the streaming feature that this technique offers, that is the suspension of the particles and the associated Brownian motion, will also allow us to derive the particle size distribution data from this apart from the particle size. Okay, so that's the beauty of the technique, that you not only get the particle size, but you can also get the particle size distribution quite easily from the same data.
Alright, that was all about the basic principle behind the DLS technique. In the next video, I'm going to show you the DLS instrument. So don't forget to tune in. And yes, please do subscribe to my channel for more exciting videos. Thank you.